In the previous section, what we did is we came up with the process diagram as well as the process schematic for the Rankine cycle with regen and reheat. What we're going to do now is we're going to go through and we're going to determine the values at each of the different states, so the property values. And I'll refer back to the process diagram and the process schematic. Whenever you're doing this, the best place to start the process is where you know the information. And usually what we'll be doing is we'll be starting right at the saturated liquid line when you're going into the pump. So this would be location 1, which on our schematic diagram would be there. So let's go ahead and start the process of determining the properties and the state information. And then we'll work our way through and eventually get to the first law. So to begin with, state 1, we can go into the steam tables, and there we're dealing with a saturated liquid. So what I would do is I would pull out the enthalpy value as well as the specific volume at state 1. And with that, what we'll want to do is we want to be able to determine the enthalpy at state 2. And in order to do that, we'll be using the steady flow equation for work into a pump. And recall that is one that we can evaluate knowing the specific volume at 1, and then the pressure change between states 2 and state 1. And so that is the work, and that work is going to be equal to the change in enthalpy between states 2 and state 1. So looking back on our TS diagram, what we're looking at here is the work going from state 2 to state 1. And that's what we've just evaluated. And so with that, what we can then do is determine the value of H2. So that gives us state 1 and state 2. The next thing we want to do is we want to determine the value at state 3. So let's look at our TS diagram. So the next state that we're interested in is right here, state 3. Again, that is on the saturated liquid line. So we're just going to use the same process that we did before. And the pressure for this one is going to be the pressure at which, let's look back on our TS diagram, that is the pressure at which we're pulling the steam off as part of the bleed stream. So that was at 0.8 megapascals. So that is the pressure that you need to look at when you go into your steam tables. Again, we'll pull off the specific volume because we're going to use the work equation again in order to determine information at state 4. Except here we have the pressure difference between states 4 and 3. So with that, we know H3, and so we can directly determine H4. H4 turns out to be... Okay, so if we look at our TS diagram, we now have state 1, state 2, state 3, state 4. The next state that we need to determine is state 5. And state 5, we are told the temperature, we know the pressure is 10 megapascals and the temperature is 550 degrees C. So with that, you can look in your steam tables, but you'll find that that is at a superheat condition or superheated steam. And so what I'm going to pull off is the enthalpy value there. And another thing that it's useful to pull off at this point is going to be, oops, sorry, there's the problem statement. One other thing that will be important to pull off, so we're trying to find information at state 5, and notice 5 to 6, 7, that is an isentropic process. So at this point, it is beneficial to pull out the entropy at state 5. So that is another value that we're going to pull from the tables. So we have the entropy at state 5. Now in determining state 6, and if we look on the TS diagram, state 6, state 7 are the same. Well, we know the entropy is going to be the same between 5 and 6 and 7, but we need to determine the enthalpy at that point. We know the pressure is 0.8 megapascals, and so we will use the entropy enabling us to determine the value of the enthalpy. And so for this, you're probably going to have to do a little bit of interpolation in the tables. But what we have is S6 is equal to S5. And so we know the pressure here, it is 0.8 megapascals. And so what we do is we look in our tables and we find that we are still superheated. And we can estimate the temperature. And the other thing that we get is the enthalpy of 6, which is going to be the enthalpy of 7 as well. Okay, so let's look at our TS diagram, see how much we've been able to extract. So we have state 5, we have state 6 and 7. Now what we still need to determine is states 8 and 9. And in order to get state 8, we know the pressure is 0.8 megapascals and it goes up to 500 degrees C. So we can go into the superheated tables and get that. And then to get property information at state 9, we're going to use the same thing that we did between 5 and 6. And that is we're going to get the entropy at state 8, which will enable us to determine values at state 9. So let's create a new page and we will do that on this new page. So we're after state 8. So this is the conditions after you go through the reheat boiler. So that is the value of enthalpy, and entropy at state 8 would be that. That'll be kilojoules per kilogram Kelvin. And finally, state 9, what we do is we use the fact that expansion from 8 to 9 is an isentropic process. Now we know, if we go back, the pressure in our condenser is 10 kPa. So what we can do is we can look in the steam tables at the value of entropy at 10 kPa. And when we do that, the value of the entropy there is going to be... And what we find is that we're in the two-phase region at 10 kPa. So we use the equation that enables us to determine enthalpy when we're in the two-phase region. And we want to solve for X9. So you see 96% is in the vapor phase. So we're quite close to the saturated vapor line, but we have 4% droplets or water in the mix, which means we're going to lose some efficiency there. And finally, H9, we can get the enthalpy value from there as well. So let's go back to our TS diagram. We've now finally determined state information at 8 as well as at 9. So with that, we've specified all of the state information. There still is some information that is missing before we can really solve the problem. And one main piece of information that still remains to be determined is the mass fraction. What percentage of mass are we stripping off and sending into the open feed water heater as well as sending through the reheat. So in order to determine the mass fraction, what we're going to do is we're going to apply the first law to the open feed water heater. Sometimes when you're solving these problems, it's kind of like solving a big puzzle. You don't always know exactly which direction you need to go as you're going through it. And so you solve one piece of information, that gives you another, that gives you another. But in this case, we will apply the first law to open feed water heater. So let's take a look at where that gets us. Now, in here, when we're dealing with a open feed water heater, we will assume that the open feed water heater is well insulated. There are no moving boundaries, and consequently there is no work being done. Kinetic energy and potential energy we will neglect. And with that, the equation we get is basically just looking at mass flux times the enthalpy coming in, and that will be equal to mass flux exiting, enthalpy exiting. So with that equation, we can look back at our schematic, and what we see coming into the open feed water heater, we have information at state 7, information at state 2, and what is leaving is information at state 3. So the two inlets are 7 and 2, and the one exit is 3. And so those are the things that we put into our equation. So what is coming in? So we get that equation there. Now, what we're going to do, we want to be able to reduce this a little further. Ideally, we want to get it to enable us to determine the mass fraction y. A couple of other things that we know through the continuity equation. Remember, that is mass conservation. We can write m dot 3 equals m dot 5. So let's take a look back at our diagram, see what that is saying. We're saying 3 is equal to 5. That's basically the mass flow rate going through the boiler is the same as the mass flow rate at 3, and it's the same as the mass flow rate at 5. So that's a pretty straightforward one. Another thing that we can say is mass flow rate at 2 is mass flow rate at 5, which is the boiler mass flow rate minus m dot 7. So let's look back and see what that is saying. M dot 7 is what we're stripping off and sending through the feed water heater. So with that comment, we were saying m dot 2, mass flow rate at 2, which is basically what goes through the low pressure turbine, is equal to the boiler feed minus what we're stripping off and putting into the open feed water heater. So we can do that with mass conservation. And we can then make substitutions into our first law applied to the open feed water heater. Specifically, what we can do is we can take this m dot 2 and we can substitute it in here. And the other thing we can do is m dot 3 equals m dot 5. That is this equation here. We can substitute that there. And what we're going to do after we substitute these, we're going to divide by the mass flow rate coming through the boiler, m dot 5. If you recall back when we defined the ratio of the mass fraction, it was expressed as being m dot 7, what we're stripping off, divided by the mass flow rate going through the boiler. And so that's why we want to divide by m dot 5. So let's go ahead and do that in the next slide. So there we have our equation after making the substitutions. Now what I'm going to do is divide through by m dot 5. So the mass flow rate going through the boiler. And when we do that, we get 1 minus y. Notice that that's the first thing, because the second term here, we have m dot 7 divided by m dot 5. That's our definition of mass fraction y, multiplied by enthalpy at 2 plus y times enthalpy at 7 is equal to 1 times enthalpy at 3. And if we look back at our schematic, we said 1 was times H3. Well, there we have 100% mass flow coming out, so that makes sense that it would be 100%. And we have 1 minus y times H2. 1 minus y times H2. And the other thing we have is y mass fraction enthalpy stream 7. And we get y times enthalpy stream 7. So it kind of relates to the mass fraction that we have. Now in this equation here, we know all of the values of enthalpy because we've determined all of our state information. So we can now go ahead and directly solve for y. And when you do that, you get the mass fraction as being 2018. So we're stripping off approximately 20% of the stream to go the steam to go into the open feed water heater. And so that will, I'll stop at this point, and then in the next segment what we're going to do, we're going to apply the first law to a lot of the different components that are within the system, and the final step to the solution will be then going ahead and trying to determine the thermal efficiency of the cycle.